Hi everyone, let me introduce ourselves. My name is Aleksei Panferov and my teammate is Ilya Trofimov. We are engineers at Sberbank Robotics Lab. Today we want to show you our winning solution for GOSEEK challenge. We want to thank organizers of such great event and especially support team. They were very quick to help. Challenges we have met here are very interesting and useful. Let's start from the task. The task was to create reinforcement learning agent which will be able to navigate in complex office environment, find and collect fruits. Agent has only 4 discrete actions. Here they are. Turn left 8 degrees, turn right 8 degrees, move forward 0.5 meters, collect fruit. On the slide, you can see the key metrics of the competition. It consists of weighted sum of 4 components. First, recall. It's a percent of collected fruit. Second, precision. It's a percent of successful collect actions. Third and fourth, collisions and actions. They are both divided by number of steps in the episode. So, the main goal is to collect all fruit in the SEM. Training environment consists of 5 different office SEMs. Each of them has unique configuration. There are office, cubicle space, restroom, break, and storage rooms. Fruit are randomly spawned throughout the environment. However, their distribution is non-uniform. Fruit are spawned only in offices and cubicle spaces, sometimes in a halfway just outside of an office. As you can see, the 5th and 4th maps are harder because of the cubicles. Simulator TESICore provides an output of 3 images 320 by 240 pixels and pose vector to TESIGIM environment. Images consist of color, semantic segmentation, and depth. Agent receives input data as a flattened vector. There are 2 different data sources in the competition, ground truth and perception pipeline. Ground truth is error-free, so it has no noise. And the perception is output of the Chimera library, so it has some errors, like in real life. You can see the differences on this slide. Only evaluation against the perception pipeline will be used to declare an overall competition winner.
Organizers kindly provided baseline solution, so we had strong starting point. It was proximal policy optimization algorithm from stable baselines library. The main idea is that after an update, the new policy should be not too far from the old policy. For that, PPO uses clipping to avoid too large update. Proximal policy optimization strikes a balance between ease of implementation, sample complexity, and ease of tuning, trying to compute an update at each step that minimizes the cost function while ensuring the deviation from the previous policy is relatively small. The agent consists of 2 networks. Network convolutional neural network for feature extraction and long short-term memory policy. It was trained with 3 million total steps. Here you can see the video of working agent. Agent behavior is not smooth, has many collisions and low precision. After we've trained baseline for 3 million total steps, we trained agents simultaneously on single scene. Therefore, we trained 5 agents on first scene with 300,000 total steps, then on second scene, and so on. Here you can see graphics of episode reward in different scenes. On third, second, and first scenes, you may see that agent is learning to collect fruits better and better, but on scenes 4 and 5, scores are a bit disappointing. So our main goal was to improve agent performance. First of all, we tried to find human performance level. So we added simple keyboard-controlled agent to be able to navigate by ourselves and collect metrics. Here you can see video of human navigation and its metrics in 2 episodes. We had not so powerful computers for learning, and to boost training speed, we have to resolve a couple of bottlenecks. First, we reduced simulator output resolution to 160 by 120 to decrease video card memory and CPU utilization. Good structured code of TESI allowed us to do this easily. After this modification, we nearly doubled learning speed, and it did not affect on agent performance. We don't know if performance would have been better if we trained our agent with 320 by 240 input. Second, GOSEEK simulator consumes a lot of CPU time. It's about 4 core per 1 simulator instance, 400%. To solve this problem, you need to disable VSync count in Unity project, recompile some parts of TESI core, and swap DLL files in simulator resource directory. Also, you need to add capture rate parameter when we are launching simulator in TESI Gym. We determined that 60 frames per second is enough for us. At 60 frames per second, CPU consuming per instance decreased to 150%. As now, we had maximum performance on our hardware. Let's talk about the most important part of our solution, construct reward function. If we want our agent to explore more spaces, we need to give it some bonuses. In this challenge, we had planar coordinate system, x-coordinate, y-coordinate, and angle. And origin was relevant for the start position. Agent has fruit collecting area, 80 degrees field of view with 2 meters success distance. So we can draw fruit collection area for one step and calculate the area. Also, we can calculate the area covered by the agent for a single episode. Maximum area covered by the agent is 340 square meters if the agent is moving only straight forward. If we use only collect, turn left or right actions, their area will be less. Usually, it is about 50 square meters per episode. Firstly, we added sparse reward at the end of episode. It seems agent has struggled with learning. After this, we've added bonuses on every step when agent explored new area. For this solution, we used Python Shapely library. Sometimes agent falls through textures and covered area starts to increase drastically. Depth info helped us to exclude rewarding in this situation.
The next step was to deal with collisions. It is logical that before the collision, there are some near objects in the field of view of our agent. So, we can add a penalty for the cases where obstacles closer than 1 meter from agent. Also, we added penalty for collisions cases, and it's bigger than the penalty for detecting obstacles. We think it is the worst case. Also, we tried to stimulate the agent to look for fruit more carefully by adding bonuses for last fruit, first collection of the last fruit or group of them will give the agent more reward. Here is the code of the additional part of our reward function. And also, you can see the different method of exploration motivation by relative distance. But it didn't work for us. On this slide, you can see the agent that was trained with previously mentioned reward function. It has quite good metrics in recall and collisions, but terrible in precision. So we decided to improve it. We added a new penalty. The main idea is to give penalty if agent tries to collect a fruit thought it isn't in the field of view of the agent. For this, we used binary masked semantic segmentation. Here you can see the winning solution at work. We doubled precision metric with this algorithm. And here is our final score on the perception pipeline. Some of ideas we constructed and checked, but think that they are not useful for training. First, penalty for useless actions. For example, collect and collect again. Turn left and immediately right. Second, penalty for approaching to chairs and tables. For example, if agent approaches chair, we kick him because he may stuck under the table. Third, using grayscale image and binary, meaning black and white masks for furniture and fruit classes as input sources instead of color image. Fourth, asynchronous advantage actor critic algorithm with recurrent policy and 5 agents on 500,000 steps didn't learn. Fifth, actor critic using Cronenberg factor trust region algorithm didn't start because of the error in the code.
In the next step, we tried to tune hyperparameters in the model. First, we've increased gamma parameter. Second, we've increased learning rate. And finally, we've added some long short-term memory cells to improve agent behavior in complex situations. By default, there were 256 cells, and we rose them up to 1024. New hyperparameters improved the agent behavior. Agent moves carefully and takes fruit with higher precision. Unfortunately, recall didn't grow. And last but not least, as it usually happens in machine learning competitions, we decided to collect our best solution together and assemble them in one model. Our solution took first place in ground truth competition, but in perception pipeline, we stuck with running status in evaluating. When we've checked our solution with perception pipeline locally, we had found some strange behavior. Periodically, agent stops in one position and turns left and right, but not in 8 degrees. Its rotation was about 140 degrees. When robot began this strange rotation, we've launched Travis and saw that image from Chimera Veo two-dimensional mesh was frozen. Also, we've checked ROS logs, but haven't found any suspicious things. This problem appears irregularly. Here are the main lessons that we had learned in this challenge. First, you should increase learning and simulation speed so you will be able to test more ideas. Second, try to collect as much information as you can. Thus you wouldn't lose something useful or interesting. Third, Use as less frameworks as you can, so you will be able to easily modify them and try your ideas with less effort. Fourth, less is more, so try to use compact neural nets if its performance is okay for you. Also, it will converge faster. Thank you for your attention. If you have any questions, we will gladly answer you. Here's our emails and GitHub link for our solution.